All right, hi everyone. How are you guys doing? All good? All right, so first of all, let me welcome you guys to Unacademy JEE English. This is a brand new channel by Unacademy, India's largest online learning platform for IIT JEE. And here, everything is being taught to you completely in English so that no student is feeling left behind. All right, so today, the topic that we'll be discussing is properties of conductors. Hi, Karthi, how are you? Uh, it would really help, Karthi, if you can tell me if my voice is loud and clear, if you can hear me properly. Just a quick check. Good evening, Saloni. How are you? Just let me know if my. All right. Thank you so much. So today we'll be talking about properties of conductors, and this is a very important topic as far as your IIT JEE Mains and Advanced both are concerned. Especially for Advanced because this topic can have some really tricky problems. Hi, Bharat. How are you? Thank you for letting me know, guys. So let's move forward. And before we start the topic, let me introduce myself one more time. So, my name is Rohit Dixit. I've studied mechanical engineering from IIT Delhi. I have more than 7 years of teaching experience, wherein I've taught at some of the biggest names in the industry. All right. And I myself was JEE rank 447, and I've already coached many students to top ranks in IIT. So, guys, I have been where you are right now. I've been through this pressure, I've been through this competition, so I really hope that I can guide you also as well because I could manage it successfully. So I think I must have done something right. Anyhow, moving forward, let me tell you something more about the Unacademy subscription and its benefits. So first, you get live classes. Second, you get to interact with your educators. Then you have live polls and leaderboards. You have test series and analysis, and you have live doubt clearing sessions. So trust me, all these plus points will give a huge boost to your JEE prep. Now, on top of all these benefits, you get access to India's best educators with your Unacademy subscription. All right. Now, how to get this subscription? It's very easy. Follow these simple steps. Install the Unacademy app. Once you've done that, go to your plus section, select your goal as IIT JEE, and click on that Get Subscription button. It's that easy. All right. Now, once you have you're getting the subscription, if you notice, the pricing is kept very modest. The 12-month and the 24-month subscriptions turn out to be the most economical. So I would advise if you guys are going for a subscription, try if you can manage these two because these two will be the most economical for you. Alright, if you take a look at the 24-month subscription, it comes at only 1500 rupees a month, which is barely 50 rupees a day. So very affordable compared to all the fees that you guys pay elsewhere. Now, this already affordable pricing for such quality education will be made much more affordable, even more affordable if you use my code RD Live to get your subscriptions. Alright, use this code, you'll get another 10% off. Alright, next, moving forward, please join us on the Telegram app using the link shown above so that you get all the notifications of all the sessions and lectures which have been conducted on the JEE English channel. Okay, so this is the new timetable that we have been following since yesterday. Okay, so go through this. Alright, if you notice that I am taking classes on Monday, Wednesday, and Friday for Target 2022, that is class 11 students. On Tuesday, Thursday, and Saturday for Target 2021, that is class 12 students. And all 6 days for Target 2022. So, guys who are just going to appear for their JEE. Alright, so see what target applies to you and remember your timings accordingly. All right. So why don't we get started with today's discussion then? Right. So today we'll be talking about properties of conductors. Now, before we do that, let's try and understand what exactly conductors are. So, what are conductors? The way we define conductors is that conductors are objects that allow free flow of electricity. Alright, so when you try to pass electricity, the conductors will allow the electricity to pass through them easily. Okay. Now, how are the conductors doing that? Why not other substances? Why is there a difference that some things allow electricity to pass through them while some other things don't? So the reason is that conductors have a special thing called free electrons. Now, what exactly are free electrons? Now, free electrons are those which are not bound to a single nucleus. So, what do I mean by that? Hi, Hariharan, how are you? What do I mean by that? See, you guys know that all the matter is made up of atoms, and every atom has a nucleus, and you have electrons revolving around it, right? So, there, something like that. Maybe two electrons here, maybe some more electrons here. So all these electrons are bound to the nucleus because there's a positive charge here and all these guys are carrying a negative charge. So there is an electrostatic force of attraction. So because of this is a very strong force. The electron is bound to go on moving around this nucleus only. It cannot leave its orbit. Consider something like Earth moving around the sun, right? Earth goes on moving around the sun, it does not get away. Why? Because of the gravity of the sun. Similarly, these electrons can only go around the nucleus, and that is why they are called bound electrons. They are bound in their orbits, they cannot leave their orbits. Okay. Now, there is a special case, however, which is of free electrons. Let's see what that is. So, consider, let's say, a sodium atom. Okay, so sodium, is a metal, is a good conductor. Alright, so sodium has 11 electrons. So 2 here, then 8 here, and then let's say 1 more here. Alright, so that is the sodium atom. I am drawing a rough diagram. Okay, so 1 electron is here. Now consider isolated. When this atom is isolated, which means it is all alone, then this guy, the electron right here, so let's denote it with some color. Then this electron, this is called the outermost electron, the electron in the outermost orbit. If this sodium atom was isolated, if it was separate, if it was all alone, then this guy is obviously bound by the attractive force of this. Then this guy will keep on revolving around this atom and cannot leave it. However, what happens when you look at a piece of sodium, a big piece of sodium, a big chunk of sodium, which has a lot of atoms all around? So consider that there is another sodium atom right next to this. Alright. So there is another atom right next to this. And this guy also has the outermost electron with itself. And similarly, imagine atoms all around this. Alright, so you'll get the picture. So consider one sodium atom here. Alright, another guy below this. So I'm just showing you these 3 neighboring atoms right now. Hi Ankit, how are you? Can we say that these free electrons are mobile electrons? Yes, you can. And I want to show you why they are mobile. How come they are moving? So imagine what happens is, imagine all these guys have their own outermost electrons. Alright. Now imagine what happens is that when this guy was moving around this nucleus, so when imagine it reaches a point here. Now what happens is that when it reaches a point here, it is obviously getting pulled by this nucleus, but you realize it is also getting pulled by this nucleus because there is a positive charge here also. So in special case of some materials, these electrons are not very strongly bound to their own nuclei. Because of which what happens is that when they are revolving around this nucleus, and suppose when it reaches here, now it may either continue to revolve around here or it may jump and start revolving around the neighboring nucleus. That is what happens. Alright. And there is an equal chance of that happening. There is an equal chance that it will continue revolving around its own nucleus, and there is a good chance that it will jump and start revolving around the neighboring nucleus. Alright, similarly, when it reaches here, imagine when it reaches here, it is being pulled by this and this, both the nuclei. So moving forward, it may either go like this or it may either go like this. So what happens is that this electron is not bound to only this nucleus. It may continue revolving around this nucleus, or whenever it gets near another nucleus in the proximity, it may jump to that nucleus, start revolving around that one. No one is present there to oppose. So then electrons can jump many times. Yes, yes, Guranj, very correctly identified. So these electrons will in fact keep on jumping, keep on jumping. Electron repulsion, yes, yes, that also, because all your metals you will see have maybe one electron in their outermost orbits or two electrons. So the electron repulsion is also lesser. So that is what makes it easier for them to jump. Okay. If imagine chlorine was there, so chlorine in any case does not exist in this form. In the form of solid, you realize the atoms get very closely packed, and that is only where this can happen. In case of say chlorine or hydrogen, they are already existing in molecules, and every molecule is very far off from each other. Okay, good Ankit. I'm glad that you got it. So what will happen is that these are called delocalized electrons because they do not have a fixed location at one place. They will keep on jumping from here and there. So all these electrons are jumping from one nucleus to another and completely randomly. So this is how it appears. If you notice metal lattice, this is how it appears. Not really, Goraj. Because they require energy to jump also. So that is completely random. That is completely random. Some guy would be jumping in, some guy would be jumping out. Realize. Suppose this guy jumped into this and maybe its own electron jumped out of this. So they will keep on exchanging energy between them. They are not releasing them like that. So even if somebody released, somebody else gained. That is why the net energy release will not happen. Okay. So you will realize all these electrons are randomly jumping all around. Alright. So this guy may be jumping here, this guy may be jumping there, this guy may be jumping there. So because of this, what you see is electrons moving all around like they've gone completely crazy. Okay. So that is why you will see an electron cloud. This red thing that you see, it's a swarm of delocalized electrons. You see a continuous cloud of electrons which is hovering around all these nuclei. Okay. So that is what is happening, and these electrons are called free electrons. Now you realize within the metal, if this was the boundaries of the metal, within the metal these guys are free to roam around anywhere. They one electron of this could have reached here, could have reached here, could have reached here. So this electron, free electron, can reach anywhere inside the metal. However, what happens when it reaches the boundary? Now it cannot jump outside still, right? Because all these nuclei together will pull it. So it can move freely inside the lattice, inside the solid, but it cannot leave the solid structure yet. Okay. So good afternoon, Vineet. How are you? So please remember that free electrons are only free to roam inside the metal lattice. Alright, inside the solid structure. They cannot, however, jump into the air. They cannot start jumping into the air. So that is the idea of free electrons. And you realize that free electrons are not bound to a single nucleus. They do not belong to any one nucleus. These electrons can hence jump freely from one nucleus to another. Alright, next. Let's see what will happen to electrons when the external electric field is absent. Alright, so here, let me see if I can show you this, because this was supposed to be a GIF which doesn't play on the PDF. So let me see if I can show this to you. This particular image shows you the jumping of electrons. So let's see if I can manage to show you that. The problem is my PPT doesn't work very fine. That is why I have to present on the PDFs. But this is one thing that I wanted to show you. Alright, let's see. Hang on for a second, guys. I'm trying to show you this GIF wherein you will see the electrons jumping. Okay. So till the time I'm doing that, why don't I see what you guys are writing? Alright. Okay. Hi Soham, how are you? Good afternoon, Vineet. Alright. So okay, this guy will crash at any time. That is why I don't present this in PPTs, but I just wanted to show this. So see, this is what is happening. You realize these electrons jumping from here and there. So this guy jumped here, this guy jumped here. That is how these electrons keep on jumping. Okay, I hope you can see those electrons jumping randomly from one nucleus to another. I mean, in this picture, it's not random because it's one pattern getting repeated. But the idea is that the jumping would be completely random. Okay, hope you can see that. So, what happens to a conductor in absence of an electric field? If there is no external electric field, then you realize then the jumping of free electrons is completely random. Why? Because imagine this guy. This guy is surrounded by this, and this. There is no reason why an electron would jump or favor jumping in any one direction or favor jumping to a single nucleus, right? It can by chance. It's just a matter of chance which nucleus it jumps to. So it may jump here, it may jump here, it may jump here, it may jump here, it may jump here. So all these jumpings are a matter of chance. There is no reason why the electrons would want to jump only to one side. That is why I'm saying that the jumping of all the free electrons is completely random. So suppose what is happening is that one guy jumps in this manner, then some other guy would jump in this manner, some other guy would jump in this manner, some other would jump in this manner. So if everybody is jumping randomly, so there will be no net direction of charge flow. I hope you realize, because anybody can go in any direction randomly. Therefore, you don't see any net movement of charges. Right? So, I have to leave the class due to some reasons. Yeah, please, no problem, Saloni. The recorded version would be there, available there, so you can, of course, always watch it later. So as I said, the jumping of these free electrons is completely random. Because of that, what is happening is when you try and see at the charge transfer happening anywhere, there is none. Alright. So there is no bulk charge transfer or accumulation of charges happening anywhere. Anywhere you see, the net charge always appears to be zero. Okay. I'm talking about not a single atom, but a slightly bigger bulk which has like thousands of atoms. Right, even a very small tiny part will have thousands, millions of atoms. So even if I look at a very small chunk, because of all the random jumpings, there will be no net charge collection happening anywhere, and there will be no net charge movement happening. Alright. So as a result, when you notice, there will be no net electric field inside the volume of the conductor. Okay. If instead electric field, we put magnetic field, then would the electrons move in a particular path, or would it be random? So Gauransh will talk about the magnetic field and its effects later. Turns out, yes, that will change the behavior slightly. Okay, that is so that will happen. If you put them in magnetic fields, then their behavior does change. But here I'm only talking about electrostatics, and this is for class 12 students, so I'm assuming they have no knowledge of magnetism. Yeah, that was the problem. That is the problem that happens with my PPT. It keeps on crashing. So anyways, back to my PDF. Won't have that problem again. So we'll talk about that when we are studying magnetism. Okay, so here let's just focus on this. So we've already discussed this. So whenever you look at any part of the conductor, what is the net electric field? The net electric field is always zero, because all the atoms at any time as an average are always neutral. I mean, imagine if this electron jumps here, then some other electron will jump here. So this atom will appear to remain almost neutral at all times, because this jumping happens very, very fast. Okay, so that is what I'm saying. All atoms practically remain neutral at all times. And that is why you don't see any electric field being generated inside a conductor. Next, now let's see what happens when you put a conductor, when you expose it to an external electric field. Okay, so the presence of the external electric field modifies the jumping of free electrons. They no longer jump randomly. Okay, so the electric force causes them to favor jumping in the direction opposite to that of the external electric field. Let's go over this point and let's see it happening here. So what am I saying? So why does it alter the behavior of jumping? So imagine if I created an external electric field here, which is in this direction. Now electrons being negatively charged, because this electric field, they will feel a force in this direction. All the electrons start feeling forces in this direction, right? So let's draw this like this. Now because of this additional force, now all of them are getting pulled towards here. Right. So imagine when this guy is rotating, revolving around this nucleus. If it wants to jump here, the energy required to jump the opposite side would be higher. Why? Because it has two things now pulling it this way. One, this nucleus is pulling it this way, the electric field is also pulling it this way, while on the other side only this nucleus is pulling it this way. So that is why this time it will be more difficult to jump towards the right. However, when it was here and wanted to jump towards the left, that would be easier. Why? Because this nucleus's hold will get weaker. Why? It is the only one which is pulling the electron in this direction, and on the other direction, this nucleus plus the electric field both are pulling it in this direction. So the electron is already feeling a net force towards left. So obviously this time when it wants to jump, it will be easier for it to jump towards the left side. And that is why you see that most of the electrons or a larger number of electrons will start jumping towards left. I'm not saying now that no electron would be jumping this side. There would be some electrons which would randomly gain that much energy also. Alright, the energy is distributed randomly also. All the electrons do not have one energy. Some end up getting more, some end up losing some. Alright. So a high energy electron may still manage to jump here. But you realize more number of electrons will find it easier to jump here. So I'm not saying all free electrons will start jumping towards left. That is not what happens. But majority starts jumping towards left, and that is why you will see a net charge transfer happening towards the left hand side. Hi Mayank, how are you? So I hope you guys got that. Now along with the neighboring nucleus pulling the electron, the electric field is also pushing it towards left. So that is why if I notice and if I see that 10 electrons jumped, now out of 10, almost 7 would have jumped in the left hand side direction. Yes, that will also happen. That will also happen. But in case of conductors, the pull of the nucleus is way greater, and that is how they can manage. That is why they can't manage all that in all other materials. Okay. So that is the property of conductors. See, conductors like sodium have only one outermost electron, right? Valency 1 or valency 2. So outermost shell only contains either 1 or 2 electrons. So you realize the repulsion is smaller. While most other non-conducting materials, they have larger number of electrons in their outermost shell. So there the repulsion would be higher. Alright, I hope you got that. There is repulsion, of course, but that repulsion is not that big because the repulsion is only due to, let's say in sodium's case, only due to one outermost electron that is repelling, but the nucleus altogether is huge. So that is pulling it. So the pull manages to overcome the repulsion. Okay. Now what happens is that all these electrons end up favoring jumping to one side, and we can see that that side will be opposite to that of the external electric field. Alright, so most of the free electrons start jumping towards this side. So imagine they reached here, now they will jump here further, right? So, and when it reaches here, they will jump further, and they will keep on jumping until and unless these electrons are reaching the surface, right? What happens when they reach the surface? They will try to jump out of the metal also, but that they can't. All the nuclei combined will hold them together. So they are stuck at the surface. They want to go out because of the external electric field. External electric field is pulling them out also. But all these nuclei combined, they are not letting them go to go out. So all these free electrons, after they are jumping leftward, would start accumulating on the surface here. Alright. Similarly, imagine the space that was created here, right? Because this free electron jumped, so obviously there was a positive deficiency which was created here. A positive charge would have come here. So an electron from the neighboring atom would jump to fill this, and which will make a positive shift here. And similarly, an electron from the neighboring atom would jump again here, and the positive charge would have shifted here. And at the end of the day, all the positive charge would have started appearing here. Alright, now because there is no electrons from here to jump and shift the positive charge further. So, because of all this jumping in one direction, all the free electrons which are jumping will eventually start accumulating here, and as a result a positive charge will start accumulating here on the opposite side. So this will always happen. Now this is called the induction of charges. Now you see net charges appearing, and this is what induction is. Okay, this is how the charges are starting to appear on the surface. Okay, this is induction. So as I said, this results in their ultimate accumulation on the surface. So alright, now the jumping is not random anymore. The jumping is favored in the direction opposite to that of the electric field. Alright, and as a result the charges are accumulating at surfaces. Why at surface? Because they have no option. They cannot go beyond the surface. They are stuck. Okay. Yes, net charge would be zero, because if earlier this didn't have any charge. So assuming earlier the conductor was neutral, then obviously no net charge can be created, right? See, if one electron shifted here, then one positive charge is left here. So always equal and opposite positive and negative will appear. So net charge would always be zero, assuming it was zero initially also. Okay. The induction is not causing any net charge to appear. It is only causing the charge present inside to get separated in positive and negative. Okay. So now you will notice one very interesting thing. Another interesting thing that you will notice is that these accumulated charges will produce their own electric fields, which will be in the opposite direction of the external E. So let's see what I'm saying, what I'm talking about here. If you notice here, I told you that negative charges are accumulating here. Alright, and positive charges are accumulating here. Now you realize these negative and these positive charges will start creating their own fields, and it is very clear in which direction their field would be. So obviously their field would be from the direction of positive to negative. So this is the direction of the internal electric field that is getting generated. We call this internal electric field. This is the field which is created by these charges. Okay. So these charges are creating an internal electric field. And you will notice that the direction of internal electric field is opposite to that of the external electric field. Now let's take a look at what the net field, what is happening to the net field inside the conductor. So inside the conductor there are two kinds of fields now. Alright, one external and another internal. So these are external fields. So this is external fields. And of course, the earlier ones are internal. Okay, so let's just draw it here. So these are internal fields. Now the net field would be a superposition of these, or vector sum of these, right? Hi Hitesh, how are you? The net field would be a vector sum of these. So imagine what is happening. Let's just say that, let's try and imagine. Okay, so there was an external field like this. Now imagine one negative charge came here. Okay, I'm only discussing when only one has come here and one positive has come here. So this would have created a very weak field in this direction. Right, because of which the net field here would get decreased slightly. Alright. So let's imagine earlier the field was like this, This is before the charges got induced. I am drawing a lot of lines to signify that the field is stronger. You know that the field is directly proportional to the density of field lines. So once this charge is accumulated, what will appear? The field would have reduced a bit. Instead of, let's say, 5 lines, you see only 4 lines left. Alright, but there is still a net electric field in this direction. So this will cause more free electrons to start jumping here. So now let's say 2 electrons come here and 2 positive charges come here. Now, since there are 2 charges, so they will create a greater field. So this field will reduce further. So as more and more charges are accumulating, this field starts reducing slowly and slowly, right? Eventually, there will come a point when the external electric field strength would become equal to the internal field strength. As more and more and more charges are accumulating on the surface, you will realize that the internal electric field will go on increasing, while obviously the external electric field is constant. So as a result, what happens to the net field? Net field inside the conductor will start decreasing. And obviously, there will eventually come a point when the internal electric field, due to all the accumulated charges, would be strong enough to completely cancel the external electric field. In that case, what you will notice that all the electric field inside has disappeared. So soon there will be a situation when there is negative charge here, there is positive charge here, and there are fields outside. But there are no fields inside. So inside all the fields would disappear. Why? Because as superposition, these two will cancel each other out. This guy will cancel this guy. Okay, I hope you guys followed that. Let me know if you followed that. I hope there is no confusion about that. So I'm saying, as a result, these charges are accumulating, all right, appearing on the surface, and they are producing their own electric field opposite to the external E. Next, I'm saying that this accumulation of free charges will eventually stop when the electric field due to the accumulated charges cancels the external field completely. Now imagine what happens now. Once this situation has arrived, alright, once this situation has arrived, that the field inside has become zero. Now, you realize all your electrons inside will go back to jumping normally or randomly. Alright, once this situation has arrived, now you realize you take an electron. Now this can jump to any nucleus again. Now it can jump to this guy, this guy, this guy, this guy. So after a certain amount of charge has already accumulated, how much, whatever is enough to cancel the external field. Now you realize all the free electrons left inside, now they go back to jumping randomly because there is no force now acting on them. So if they start go back to jumping randomly again, now I will stop seeing any further movement of charges. So once this situation is achieved, I do not see any further movement of charges, and that is what I'm saying, that an electrostatic condition is achieved here. Alright, so an electrostatic condition is achieved. Electrostatic, when we say about electrostatic, we mean that there is no charge transfer happening, right? All the charges are stationary. I'm talking about on a macroscopic level. On a microscopic level, yes, these electrons are jumping. But on a macroscopic level, if I look at a slightly bigger picture, then there are no charges moving anywhere, and that is why I say that electrostatic condition has been achieved. Okay. So I hope you guys followed what happened to a conductor when it was kept inside an electric field, what all it went through, why the charges accumulated, till what time the charges accumulated, and when will the charge accumulation stop. Please let me know in the chat if everything is clear. You can also let me know if you want some point to be repeated one more time. Alright. So, let me know quickly so that we can move forward with the discussion. See, you need to follow every small little point, every small little logic, because all the properties will be linked to this. Okay, so great. Thank you, Garansh, for letting me know. Next, now let us see the properties of conductors in electrostatic conditions. So please remember this, that we are only talking about the properties of conductors in electrostatic conditions. Please remember this. We are only talking about the properties in electrostatic conditions. Electrostatic condition means that the net charge transfer has stopped. There are no charge transfers happening anymore. So the first property that you will notice is that the net E inside the volume of the conductor is always zero. Alright, so any condition you take, any condition, doesn't matter how we got there. If at any time you look at a conductor, so consider at any time I'm looking at this conductor and I see that there might be some charges on the surface. I don't know whether they are positive, they are negative, how they are appearing. So some charges are there on the surface and I see that no charge transfer is happening. Let's imagine no charge transfer is happening. So in the example shown, this guy has a net positive charge. Maybe that's because I gave it some positive charge, or yeah, that might be the case. Or maybe I took out some negative charge, whatever. So the point is that I'm looking at an electrostatic condition. Electrostatic means that there are charges present and I don't see the charges moving anywhere or shifting anywhere. So obviously the first thing I can conclude that if a conductor is in electrostatic condition, if there are no charge movements happening anywhere, which means it can mean only one thing, that the E inside has to be zero. There cannot be any electric field inside. Why? Imagine had there been an electric field. If there was an electric field inside. So imagine if there was an electric field like this. So what would have happened? Free electrons would have started jumping. So I would have seen the positive charges disappearing from here and more positive charges appearing here. But since I don't see the charge distributions changing, since I don't see any charge movements happening, so this cannot be the case. Alright, any kind of electric field would have started making those free electrons jump and would have resulted in charges moving from one place to here, while we said we are only talking about the electrostatic condition. So an electrostatic condition would be possible only if the net electric field inside a conductor is zero. Okay, so remember this. So the moment you see electrostatic condition, you can immediately conclude that the net electric field inside the conductor has to be zero. Second, now since the net electric field is zero, you can say that the entire volume of the conductor is equipotential. Okay, I am saying the moment you see that a conductor is in electrostatic condition. The moment you see that a conductor is in electrostatic condition, which means that there is no charge movement happening anywhere. So I can immediately conclude that the electric field inside, the net electric field inside must be zero. Because if there was an electric field inside the conductor, then my free electrons would have started jumping in the direction opposite to that of the electric field. And I would have seen a movement of charges. Alright, but since what I see is electrostatic condition, which means no charges are moving anywhere, so that is only possible if there was no electric field. Okay, I hope you got that. I mean, imagine the other way around. If there was an electric field, then free electrons would have started jumping opposite to the direction of the external field and I would have seen charges moving. But I am talking about when I saw electrostatic condition. When I saw the conductor, I realized that it was electrostatic. There was no charge transfer happening anywhere. So if I see electrostatic conditions inside a conductor, I can immediately conclude that the net electric field has to be zero. Alright. Good. So obviously, I know that if my net electric field is zero, so imagine let's make a conductor. So inside the electric field is zero, then obviously if I am taking a charge, how do I define potential difference? Potential difference was the work done in moving the charge from some point A to point B. Right, so if I move a charge from any random point A to any random point B, so obviously there will be no work required to move this charge because there is no force that this charge is feeling because there is no electric field. So the charge can move freely inside, right? So that is why I can say that the potential of all these points would be equal. So this entire region would be having the same potential. Please remember, I think we had already discussed this in my previous video, that any region where there is no electric field would be an equipotential region. So since the entire volume of the conductor becomes becomes an electric field free zone, so to say, it will be an equipotential region. Alright, all the potentials of all the points inside the volume of the conductor would be same. Okay. Next, I can say there is no net charge at any point inside the volume of the conductor. Let's see how we are saying that. Now that can be simply concluded from Gauss theorem. Okay. So imagine you had a conductor. Alright. So here's my conductor. And let me make an imaginary Gaussian surface inside. So let this be my random Gaussian surface. So if I take this Gaussian surface, so what I'll realize is, what is the integral of closed integral E dot dA? It will be 0. Why? E is 0 at all points. So if E is 0, integral of E dot dA would also be 0, which means Q enclosed would also be 0. So the charge enclosed inside this volume would be 0. Now I can go and make such Gaussian surfaces anywhere, but wherever I make, I will always find this situation to be true, which means the charge enclosed has to be always 0. Alright. So I cannot have any net charge sitting inside the volume of the conductor ever. Alright, because that will mean that the Gauss law is getting violated. Alright, so in accordance with Gauss law, I will realize that no net charge can appear inside. Okay. Next, any net charge, whether it is given externally, whether you are giving it a net charge or it is induced, can only appear on the surface. So we already talked about the induced charges. We already realized the induced charges get stuck on the surface because they cannot move any further. How about when I give a conductor a charge? Let's see what happens then. So imagine again, there was a conductor, and imagine what happened if I placed a positive charge somewhere inside. So let's say I place a plus Q charge here. If I gave it a plus Q charge and I placed it somewhere inside, now what happens is that, let's see, interestingly, it will create an electric field, right? It would have created electric field. Now because of this electric field, what would happen? All the free electrons would start moving in the opposite direction of the electric field. So what you will notice is that a lot of free electrons now, so free electron here would start jumping in this direction, free electron here would start jumping in this direction, free electron here would start jumping in this direction. So all these free electrons would start jumping towards this Q and will eventually start sticking on this plus Q. Alright, if they will start sticking on this plus Q, I will see a net positive charge due to all these electrons are getting moved. So there must be a positive deficiency left here, which will be filled by an electron here. So I will see a positive charge appearing here, and a positive charge appearing here, and a positive charge appearing here, and so on. Now, till the time any net charge is present inside. See, when plus Q was there and a lot of electrons got glued to this or got stuck to this, surrounded this, then the net charge is reducing. But till the time there is a net charge, there will be an electric field. As the net charge is reducing, the electric field would also be reducing. But as long as there is any electric field, the free electrons will go on jumping, keep on jumping. Ultimately, how much? Till the charge of all the jumped electrons would be equal to minus Q. Right? So free electrons keep on jumping till they can completely cancel out plus Q. So till they completely cancel out plus Q charge. So when enough number of electrons have jumped inside so that this starts becoming zero, then you will realize that this field will start fading away. Alright. So I don't know how to make this fade away, but that is what will happen. Alright. So this will start fading away. So slowly and steadily this starts fading away. Alright, and eventually the moment this happens, all the electric field would be gone, and you would have realized by that time all the charge would again come to the surface. Alright, so any charge that you give will always come to the surface only. It won't stop anywhere else. The only place it can stop is at the surface. Alright. So I hope you guys followed this. So this will further reduce, go on reducing as the charge is getting collected. Eventually it will become zero, and when it becomes zero, you would have noticed that there is no plus Q left here. This would be gone. This will fade away, and all the plus Q would have come on the surface. Why plus Q? Because to cancel the plus Q inside, minus Q charge would have stuck on it, right? Or electrons, enough number of electrons which have minus capital Q charge would have gotten stuck to it, which would result a plus Q charge appearing on the surface. That is why you see that in electrostatic condition, again, all the charge plus Q would have come out on the surface. Okay. So I hope you guys followed everything that we talked about on this page. Please let me know if there is any confusion, because you need to follow all the logics. Everything is very logical and connected. If you follow the logics, trust me, you will not have any problem as far as the properties of conductors are concerned. Otherwise, trust me, the problems related to conductors are the biggest nightmare in electrostatics. Alright. Please write in the chat if you followed all the discussion. Please write all clear in the chat. And if there was any part that you didn't follow, then also let me know. I can repeat that. So I'm waiting for your responses, guys. Please give me a quick response so that I can move on. And start being more interactive during the session, guys. Trust me, it will benefit you more if you are more interactive. You will feel more involved. You won't be distracted easily. Okay, the positive charge holes would have charge there. Then plus Q is gone. Then to the holes would go the charge. How will that charge go? Oh, that is what I'm saying. So whenever there was a hole here, this will be filled by a neighboring free electron. A neighboring free electron would jump to fill this. See, this guy, this hole is getting filled by this guy. Similarly, any hole created here would be filled by a neighboring electron. However, when this guy reaches here, when this guy reaches the outside, now there is no one who can jump in and fill this, right? As long as you are at a point inside, so any hole that is getting created here would be filled by a guy jumping from here. Alright, so a neighboring guy would jump and fill that hole. And that hole would get shifted here. I hope you realize what I'm saying. So anytime, because an electron jumped, imagine there is a positive charge that is created here. Immediately another electron will jump here, and this positive charge would disappear, and a positive charge would appear here. The moment that happens, another free electrons from the neighboring atom will jump here, make this guy disappear, leading the positive charge here. Finally, the surface free electron will jump here, this guy will disappear. So all these holes that are getting created inside are also disappearing. And ultimately, this positive charge is appearing on the surface. So it keeps on shifting. This charge of the hole keeps on shifting, and ultimately it ends up on the surface. Now you realize that it does not have anybody to jump to. So there is nobody available to jump and fill this hole. So this hole finally rests at the surface. Okay, I hope you got that, Gauranj. Did you get that? So ultimately, this can only, the positive deficiency of electron can only, you know, ultimately appear or finally end up on the surface. So that is its final destination. Okay, great. So let's move forward then. Now, we've already talked about this. Okay, I wanted to show you why the Q enclosed is 0. We have already talked about this. When you take any Gaussian surface, you will realize the integral E dot dA is 0, which means Q enclosed is 0. Alright, next, let us see what we have discovered so far. What else can be judged? So the first thing, I can say that the net E at any point on the surface of the conductor is always perpendicular to it. Now let's see why I'm saying that. I'm saying that the net E at any point of the conductor is always perpendicular to it. So I already discussed that there is no net E inside a conductor. So any net E would be on outside the conductor, okay, on the surface at least, either on the surface or outside at some point, right? Just hang on a sec. Yeah. Now let's see what happens. I am claiming that at any point, if you go to this point, it will be perpendicular. If you go to this point, it will be perpendicular. Why? So let's imagine an alternate scenario. Let's imagine the net electric field was in some random direction. It made some angle theta. Okay, it was not perpendicular. I am hypothetically discussing a case. I am imagining a case that where the E can have any direction. So I have randomly drawn E at an angle theta with the surface. Then what I can say is that this guy would have two components, one this guy and one this one. Right. So what do these components are trying to do? So this component, you see, will try to pull this positive charge outside. But that cannot happen. No charge can leave the volume of the conductor. Right. Or I can say that this guy is trying to essentially push the negative charges away. So now since there are no, there is already positive charge and there is no negative charge which can fill this hole, so this cannot move outside. Alright. This electric field would have tried to move the hole outside, but that is not possible, so nothing is happening. However, how about this guy? Now this electric field would have caused an electron from here to jump from to here. Now that was very possible, right? So if there was such a component of electric field present, it would have caused this guy to jump here. It would have caused an electron from here to jump here, and you would have seen that this charge would have disappeared and an extra positive charge would have come here. So what you realize is that the charges would be seen shifting then, right? These charges would start shifting in this direction. Positive charges would start shifting in this direction. That is not a problem. Inside a conductor, on the surface, the charges can shift. They cannot move outside the volume, but on the surface, they can shift from one place to another. So if there was a component of electric field which was parallel to the surface, you would have seen the surface charges being shifted from here and there. Either they would start shifting rightward or leftward depending on which direction your E component was. If your E was like this, having this component, then your charges would start shifting like this. If your E was like this, having this component, then your charges would start shifting like this. But the bottom line being, if there was a field component which was parallel to the surface, alright, then it would start making all these charges shift along the surface. But why is that a problem? The problem is that I am talking about electrostatic conditions. So always remember, that is why this is very, very important. Now I am only talking about electrostatic conditions. Otherwise there is no problem. There could have been a tangential electric field and the charges would have simply shifted from one point to another, which I don't mind. But here, since I am only talking about electrostatic condition, which means that no charges are shifting anywhere. Okay, so if no charges are shifting anywhere, then I have a problem. Then this guy cannot exist. Alright, if this guy exists, it would move charges. And since there are electrostatic conditions, then I can now conclude that there can be no component of electric field parallel to the surface. Why? Because that would have caused shifting of charges, and I don't see any shift of charge. Because we see the conductor in electrostatic condition. That is why I can conclude that the net E has to be only perpendicular to the surface. Okay. So once I conclude that the entire E is perpendicular to the surface, the next immediate property I can conclude is that the entire surface would be an equipotential region. How? Let's see. Obviously, now what happens if you want to move a charge from here to here on along the surface? So from point A to point B. So you realize everywhere the field is perpendicular. So what is the work done by electric field? The work done by electric field is zero. Alright, why? Because E and hence the force of electric field is always perpendicular to the displacement. Here the displacement is in this direction. The force and the field would be here. Similarly, when I move here, the displacement is in this direction and the force or the field is perpendicular. So I realize that the work done by electric field when I move any charge from any one point of the surface to another, the work done is zero. Now work done I know is delta V over Q by definition. So since this is zero, so I can say that delta V between any 2 points is zero, which means the entire surface of the conductor is an equipotential surface. The potential of all the points on the surface are always equal. Okay, so that is what I'm saying here. Next, I'm saying the magnitude of electric field at any point of the surface is E equals sigma over epsilon naught. So I know about the direction. The direction is perpendicular to the surface. Now I am telling you that the magnitude is also known. The magnitude I can say as sigma over epsilon naught, where sigma is the charge density at a given point of the surface. So imagine if I had to find the strength of E here, then I would put the value of sigma here, that in this small region, what is the sigma? Similarly, if I wanted to find the electric field strength here, then I would find the value of sigma here, which is the charge density in the small region there, and I put all these values here and I can find the corresponding electric fields. Alright. Now, of course, if it was a perfect sphere, and a charge was given to it, you know that it distributes uniformly, then sigma is constant, alright. But that may not be the case all the time. What happens if I have a weird object? Okay, let's try maybe something else. How about an oval? So what happens if you had an oval shaped conductor? Now you will realize that the charges, if I give this also a plus Q charge, the charge distributes itself slightly differently. You will see a small charge distribution here and bigger charges here. The density would be bigger here. We will talk about this, but in this particular case you will see that the sigma would be different at all different points. So if you wanted to calculate the field here, let's say E1, then you realize you take a small portion here which has a charge density of sigma 1. If you wanted to find the electric field here, E2, then you consider the charge density of this point sigma 2. You substitute these values and you get the expressions for E. Distribution would be uneven in oval shape. Yes, Gauranj, that is what I am showing you. You will have more charges concentrated here and fewer charges here. The density would be lesser. As you can see also, sigma 1 would be less than sigma 2. Okay, we will talk about this, why this is happening. Alright. But as of now, what I wanted to tell you that if you want to calculate E1, then you substitute sigma 1. If you want to calculate E2, then you take the value of sigma 2. So wherever you want to find the field in the conductor, take the charge density of that point. Okay. So let's move ahead. Now there's a proof. Why or how do I say that E, the magnitude of E is sigma over epsilon naught? So proof is as follows. What I am doing is, this is a conductor which has some random arbitrary shape and I am considering and I want to find the electric field at E. E here. So what I did was I took a very small portion of the conductor, alright, a very small portion which has a area dA. You remember, if I'm writing the area as dA, the area has to be small. Now, okay, I am taking a Gaussian surface which is here. This Gaussian surface is, I can take roughly as a cylinder. I have taken this as a cylinder. So I have taken an imaginary Gaussian surface which is a cylinder. Alright, cylinder having a cross-sectional area dA. Alright, and this is enclosing dA of the conductor also. Now let's see, if I wanted to find the net flux passing through this. Alright, then how do I do that? I can divide this into three surfaces, right? I can divide my conductor into three surfaces. Let's call this surface number 1. Let's call the curved part surface number 2, and let's call the third part surface number 3. Now you will realize what will be the flux through surface 3. It will be 0. Why? It is lying inside the conductor, and inside the conductor E is 0. So here you realize E is 0. Alright, E anywhere is 0. If E anywhere is 0, which means integral of E dot dA for this surface would be 0. Alright. Similarly, on the curved portion, either I can say that on this curved portion it would again be 0. Why? Because here also E is 0 and here also E is 0. So the flux through this curved part is also 0. Yes, Gauraj. How about the part of the curved cylinder which is lying outside? Now outside part, you realize that everywhere E is perpendicular to the surface. So E is like this. Alright. So you have your E's like this. I have denoted this in orange. So let's stick to the orange. So E is like this. And how about the area? Area here is like this. Area here is like this. So now again I see that the area vector is having 90-degree angle with the electric field. So this is the directions of dA vectors, this is the direction of E vector. So you see at every point of the curved surface, the angle between dA vector and E vector is 90, and hence their dot would be 0. And that is why I can say that for surface 2 also, integral of E dot dA would be 0. Why? Because in the dot product, I always get the term of cos 90. So now, the only flux that can be there has to be from surface A, and that is very easy to calculate. From surface A, I realize that the area vector dA would point like this, and electric field is pointing like this. So the angle between the dA vector and electric field vector here is 0. So for surface 1, if I want to calculate integral of E dot dA, then what do I see? I will see E times dA into cos 0. So this is my integral E dot dA. Now this is already a very small portion, so E can be assumed to be constant. That is why I am just writing E times dA. That this area is so small dA that I can imagine that E here and E here and E here. E over the entire area is almost constant, okay? As I assume that the sigma is constant. No, for the outer surface one it will not be. For surface number 1 it is non-zero. You get EDA. Now the net flux through my Gaussian surface would be the sum of fluxes through all these surfaces. Alright, so that is the net flux through my enclosed surface. So what I can say is that the closed integral of E dot dA will reduce to E times dA. Alright, once I know that, I know from Gauss Law, next I can say from Gauss Law, this should be equal to E enclosed over epsilon naught. And how about E enclosed? How much charge got enclosed? So I will say, okay, an area dA got stuck inside my Gaussian surface. The area of the conductor that got stuck inside my Gaussian surface was dA. and the charge density was sigma. So how much charge got stuck inside my Gaussian surface? It would be sigma times dA. So Q enclosed is sigma times dA. The moment I substitute this value, I will realize this dA and this dA cancel out, and I get the expression E equals sigma over epsilon naught. Okay, please go through this one more time, and hopefully this should be clear to you. This is an easy proof. There's nothing too difficult about this. So just go through this once. Make sure it makes sense. Okay, this is an important result. You need to memorize this. Alright, E equals sigma over epsilon naught is a very important result. You need to memorize this. Okay. So let me know fast if you have understood the proof so that we can move forward. Alright, great. Next, let's see some more properties. The potential at any point in the volume of the conductor is the same as the potential at any point on the surface. I mean, that is very simple to see if you had a conductor like this. Now, how do you define the potential of some point here? So, the potential of point P is defined as the amount of work required to get a +1 coulomb charge from infinity slowly to this point, right? That is how you define the potential of a point. The amount of work required in moving a 1 + 1 coulomb charge slowly from infinity to that point. Now, imagine you brought it to a point on the surface first. Let's call that A. So the amount of work that it took for you to bring it from infinity to A, that would give you VA. Right, this work is VA, potential of A. Now, once your charge has reached A, now from moving from A to P, the work required is 0. Why? Because there is no electric field inside the conductor. So you realize the net work required here that would have been Vp. And now I can say that Vp equals VA plus 0. So Vp equals VA. You know that all these points on the surface are at the same potential. So the potential of A, B, C, all these guys would be the same. Similarly, inside also we had concluded that all the points are at the same potential. So you have L, M, N, O, P, any points. These are also on the same potential. So all these guys, all these A, B, C, L, M, N, everybody would be exactly at the same potential. So potential everywhere inside the conductor would be the same as the potential on the surface of the conductor. Next, any electric field lines will always be discontinuous at the surface of the conductor. Please remember this. These field lines have to be discontinuous because there can be no net external field. Now please remember that everything, again and again, let me remind you that everything is being described under electrostatic conditions only. It is only under electrostatic conditions that E must be 0, and hence all this must follow. Okay, please remember that. I remember one student asked me that if the E inside a conductor is always 0, how does the current move inside conducting wires? So when you're talking about current and electricity, and when current is flowing through a conducting wire, then you don't have an electrostatic condition. The E is 0 only for electrostatic conditions. Alright, when current is flowing, there is no electrostatic condition. I mean, imagine what is happening when current is flowing. Let me show you quickly. Imagine this was a conductor. Alright, now imagine there was a battery. So what this battery is doing essentially is giving positive charges here and negative charges here. This is creating an external field here. Alright, creating an external field. When this external field is getting created, what you know is your free electrons start jumping. So free electrons start jumping. As a result, a negative charge starts appearing here and a positive charge starts appearing here. But I told you, when does the electric field die down? When enough negative charge is accumulated here. Now the problem is, that this battery will provide more positive charge here and make this disappear. Alright, it will start making this disappear. Similarly, it will provide more negative charge on the other side and it will start making this accumulated charge disappear. So the battery, what that is doing is, it is not letting the charge accumulation happen. The moment charge accumulation starts happening, the battery goes and removes it. Okay, it supplies more charge. Or it supplies more charge. Basically, it is causing the charge to flow. It is taking out these positive charges, flowing it, and making them come here. That is why the net charge, enough charge can never get accumulated, and hence the electric field can never go zero inside, and that is why you will see charges will keep on jumping, keep on jumping. These free electrons will keep on jumping, and due to this jumping of these free electrons, you will see a net current flowing in the conductor in this direction. Okay, so that is how the current flows. In fact, what battery is doing is, battery is not letting the conductor achieve electrostatic condition, and that is why you will see a net electric field when you're talking about current electricity. Alright. So let's move ahead. Next, we need to talk about the charge distributions of in conductors. So this is where you have all your problems. This is where all your questions are asked in JEE Mains and Advanced. So they show you conductors and they ask you, okay, these charges are given, how will the charges distribute? Alright. So first we are taking the simpler case where the conductors have no cavities. So let's see how that happens. Now, in case of conductors with no cavities, which means they have no holes inside, they have no spaces inside, the net charge will always completely appear on the outer surface. Alright, okay, there is only one surface because there are no holes. So all the net charge, any charge that is given to you will always appear completely on the surface. I have already talked about the logic of this, okay. So I have already talked about the logic of this. If this charge is free to distribute itself, that is no other external E is present, then sigma of this charge distribution at any point of the surface follows the rule sigma inversely proportional to R, where sigma is the charge density of any small part of the surface and capital R is the radius of curvature. I hope everybody knows the radius of curvature. So what I am saying is that one, all the charges are appearing on the surface. Second, the claim that I am making is that the distribution of charges would be such that the sigma would be inversely proportional to R. Alright, inversely proportional to R. So here, consider this portion and this portion. So this guy obviously has a bigger radius of curvature. Radius of curvature meaning you can imagine this to be a part of some imaginary big sphere. Similarly here you can imagine it to be part of a sphere. So this obviously seems like a part of a smaller sphere. This seems like a part of a bigger sphere. So the radius of this sphere, imaginary sphere of which you can consider your portion to be a part of, is called the radius of curvature. So radius of curvature you will see is more for, if this is R1, the radius of curvature for this part, and the radius of curvature for this part is R2. You can clearly see from the picture that R1 is greater than R2. As a result, what you see is that the charge density here, the charge is scattered more here and it is collected more here. Right? The charge density is higher at a point where the radius of curvature is smaller. Now, please pay close attention. Oh, I'm good, Roshan. How are you? Thank you for asking. Please pay attention that there is a condition to this, that the charges must be free to distribute themselves. That is, no external electric field must happen. So always remember that this is valid only under this assumption. This is only valid under the condition that there is no external electric field to influence the movement of charges. If the charges are free to distribute themselves, then they distribute like that. Right? Why is that happening? That happens to make sure that the conductor is equipotential. See, if you remember, I can prove this also. If you remember, so let's treat this as my sphere 1 and this as my sphere 2. So this portion was a part of this sphere 1 and this portion was a part of sphere 2. Okay, so what is the potential of a sphere? If you remember, I hope you guys remember, potential of a sphere was kq over r. Right, so what I can say is that I can write k as 1 over 4 pi epsilon naught r times q, and I am multiplying and dividing both the sides with r. I am multiplying the numerator and the denominator with the r, with the idea that what is 4 pi r square now? 4 pi r square is the area of the sphere, right? So I can rewrite this as q times r over pi epsilon naught a. I hope everybody followed this. I've just rewrote this in this form. What is q over a? Q over a is sigma. So I can say that the potential of any sphere is sigma times r over epsilon naught. Now I know if I consider all these, so here the charge density was sigma 1 and the radius of curvature was sigma r1. Here the charge density was sigma 2 and the radius of curvature was r2. Now imagine, I can imagine that they were parts of two different spheres, and I know that these 2 points have the same potential. If the potential here is V, the potential here is also V. Why? Because there are 2 points on the surface of a conductor, and all points on the surface of a conductor have the same potential. So I can say that because of this, sigma 1 r1 over epsilon naught should be equal to sigma 1 r2 over epsilon naught equals V. And V for any 2 points would be constant. And hence I can say that sigma is inversely proportional to r. I hope you realize, because the product of sigma and r has to be a constant. If the sigma is more, the r has to be less, or the other way around. If the r is more, the sigma has to be the less. So that is why it follows sigma inversely proportional to r, to ensure that the potential at different points is the same. Next, what I am saying is that in presence of external electric field, the charge will distribute itself to ensure that the E inside is 0. That is the priority. Please remember, the first priority is always to make sure that no electric field can enter the conductor. So let's see an example of that. So this is the example. The net charge is 0, but there is an electric field. It is kept in an external electric field. Now you realize that R everywhere is same. R here is same as R here, right? However, somewhere you see negative charge density, somewhere you see positive charge density, and you will also notice that the charge density would be higher here and the charge density would reduce here. So the charge will mostly be accumulated. Negative charge will have higher accumulation here, and as you go away from the center, the density would reduce. It would become 0 somewhere. Not saying perfectly here, but somewhere it will become 0. Here it will become 0. Then it will start becoming positive, and the charge density of these positive charges would be highest here. Alright. So at the diametrically opposite ends, you will see highest charge densities. The charge densities are changing. However, you notice that the R everywhere is same. The radius of curvature everywhere is same. Still you are getting different sigmas. Why? Because here it does not follow the first law. Now please notice that this will still remain equipotential. Why? Because this electric field will be causing electric potential difference also. Alright, this field will cause different potentials at this point. So the net potential would come by the sum of potential due to this electric field and the potential due to these charges. So the net potential will still be the same. Don't worry about that. Earlier, to make the net potential same, it had to follow this, but here this guy is also involved in creating potential. So there are external regions also why the potential is getting created. That is why this does not need to be followed now. Alright, there is no need for this because there is a third party also creating potentials. So first it needs to ensure that electric field lines are not entering. The moment it ensures that, the potentials turns out are taken care of by themselves. Alright, so please remember this. So this is valid only when there is no external field or the charges are free to distribute themselves. In case there is an external field, you will notice that this does not follow. Alright. So these are the two important things that you needed to remember. Now let's talk about charge distributions of conductors with cavities. So what are the key features of this? So no charge. So there are two conditions. In first condition, there is no charge placed inside the cavity. Then in such a case, any net charge will appear only at the outer surface and E inside the cavity would be 0. So let's imagine you had a conductor and you had a hole inside here. And you're not putting any charge inside the cavity. Now, any charge that you give the conductor will always come out on the outer surface. How can I say that? That is very easy to prove. Imagine some of this charge also came on the inner surface. See, I already know that there can be no charge inside the volume. But you could have argued that there could have been some charge inside also. Maybe, just maybe, some positive charge came here also. Why is all the positive charge that I have given this guy going only on the outer surface? Maybe some charge comes here. So, okay, let's imagine that happens. Now the problem is, if I consider a Gaussian surface like this, so what happens to this Gaussian surface? This entire Gaussian surface is inside the volume of the conductor. Alright, so this is my Gaussian surface. Alright, and I can say that for this Gaussian surface, what is the closed integral of E dot dA? It is 0. Why? Because E inside everywhere is 0. Because everywhere E is 0. So since my Gaussian surface says that the net flux is 0, that leads me only to one conclusion, that Q enclosed has to be 0. There is no other choice. So since Q enclosed has to be 0, that this is not possible. These charge accumulations are not possible. Any charge that has to come will come only on the outer surface. Alright. Next, I can say that the electric field inside the cavity will also be 0, obviously. So once there are no charges here, there can be no field inside the cavity also. There is nobody creating an electric field here also. Okay. Again, you can say that from the Gaussian surface, Gauss law only. You can keep on taking random Gaussian surfaces. You realize that the net charge enclosed is 0. Why? Because there is only empty space there. So if there is no net charge enclosed, the net flux has to be 0, which means the E has to be 0 at all points. Alright, so remember this. So in case there is no charge present in the cavity, all the charge that you give will only appear on the outer surface and there will be no electric field not only inside the volume of the conductor but also inside the cavity. Inside the cavity also no electric field will reach. Okay. Okay, next is the interesting part. If a charge were placed inside the cavity, then what happens? So here I have taken such an example. Alright, here I have taken a charge and put it in the hole. Okay, now what happens? So a net charge equal and opposite to the charge present inside of the cavity will appear on the inner surface of the cavity. So my claim is that if I put plus Q charge here, then now the inner surface will get a minus charge and this net minus charge will be minus Q. How can I say that? That is very easy. Again, so this is the hole inside the cavity and this is the outer surface. So I take a Gaussian surface. I am drawing a Gaussian surface, Gauss surface inside the volume of the conductor. So this is a Gaussian surface such that this entire thing lies inside the volume of the conductor. Okay, this lies between the cavity and the outer surface. So, in case of electrostatic conditions, I know that E has to be 0. So if the E has to be 0, which means the flux through this Gaussian surface is 0. If the flux through this Gaussian surface is 0, then the net charge enclosed has to be 0. Now I know there can be no charge here, here, here. So no charges can be accumulating here. The only charge accumulation that is happening is on the surface. And inside there is already plus Q. So to ensure that the net charge enclosed is 0, the charge accumulating on the surface has to be minus Q. Alright, there is no other option. So the first thing I realize is if I keep a Q charge inside plus Q charge inside, then a minus Q will appear on the inner walls of the surface of the cavity. And similarly, if I put a negative Q charge, then a plus Q charge would have appeared on the inner surface of the cavity. Alright. So as mentioned here, this happens in accordance with the Gauss theorem. Now a charge ensuring conservation of net charge will appear on the outer surface. So if I am telling you that, let's say initially my conductor was neutral, if that was the case, then I have got minus Q charge which got accumulated on the inner surface. Now the net charge has to be 0, that is why a plus Q will accumulate on the outer surface. So that plus Q here and minus Q here, the net charge obviously cannot change because of conservation of charge. The charge, if minus Q is coming, where did it come from? It would have jumped, it would have been the free electrons would have jumped inside, and that would have left an equal deficiency of electrons elsewhere. So if negative Q is appearing on the inner walls, then a plus Q has to appear on the outer walls of the outer surface to allow conservation of charge. Okay. Next, the charge distribution of the charge inside the cavity will be determined by the position of the charges inside the cavity. Please remember this, that inside, the charge that is coming up inside is not free to distribute itself. Okay, why? It has its first priority is to block the field of the charge present inside the cavity. So let's take a case. There is a conductor, there is a spherical cavity. For the sake of simplicity, I am taking a spherical cavity. So if plus Q was placed perfectly in the middle, then I know it would create an equal electric field everywhere. And then I know that all the charge that comes inside. So if this is plus Q, so assuming this charge is plus Q, all the charge that will appear inside would be distributed evenly. Alright, why? Because everywhere equal amount of electric field needs to be blocked. What happens when I shift the position of this? Let's see. So you still have the same spherical cavity, but what happens if I keep Q here? Then you realize now what do you realize? That there is more electric field reaching these parts and lesser electric field reaching these parts. So more charges will come here to block this field. So in this case, what you will notice is that here more number of negative charges will start appearing, and here lesser density of charges will be seen. Only because I changed the position of the charge inside. Obviously, the net electric fields would not look like this. The net electric fields would become perpendicular. So finally you will have, because of the net electric field would be the electric field of these and the electric field of this. Here I am only showing you the electric field of the inner charge. The net electric field would be a vector sum of the electric field of both these, and that will take such a shape. That will start becoming perpendicular. Okay. For a conductor, I know the net electric field can only be perpendicular to the surface. So these lines should be curved and always become perpendicular. But I was only showing you the field due to the inside charge. So that is how you know that now the charge distribution will change. And so you can accordingly decide the charges that are appearing on different surfaces. they will depend on the position of the charge placed inside the cavity, because their primary aim is to block the field of this charge from entering the volume of the conductor. Okay, so I think that is it for today. I think I had a couple of points which I wanted to discuss and a couple of examples which I wanted to take, but we are running out of time already. We have reached 1.5 hours of our session. So I'll take your leave. There's only a couple of points which were left, which I'll discuss tomorrow, and then we'll take up those examples also. Till then, go through everything that I've told you in this video. Trust me, you really need to understand every concept. If you understand all these concepts, every property follows logically, and trust me, then this electrostatics part will be easier for you. So before I take your leave, let me remind you that you can get your Unacademy subscription using following simple steps, and once you have taken the when you're ready for your subscriptions, you can use my code RDLive to get your subscriptions. This will give you additional discount. It will make the already affordable pricing even more affordable. Okay. So if you liked today's video, if you thought you learned new things, then please press the like button and share it with your friends. Please, guys, you have to share it with more and more people. Unacademy is providing free education, good quality content for completely free. So we want most of the students to benefit out of this. Okay, so share it with as many friends as possible. Also, press the bell icon to get notifications of all the lecture schedules and sessions. Now, the PDF of all the slides used in this lecture will be available for download by tomorrow. So come back, check out the description box, and you can download the PDFs. Now, please remember the new timetable. These should have been put up all your. So please remember that the timetable has gotten updated, and make sure you're following the new timetable and not missing out on any class. Now, also remember, you can join us on the Telegram app. Once you do that, you will automatically get the notifications of all the lectures. In case you're not getting, because some people told me that they don't get notifications even when they have subscribed to the JEE English channel. So in that case, you can take this one extra step. Join us on the Telegram app also. Now, before I leave you, one more time, let me remind you that my code is RDLive. If you like studying from me, if you want me to be your guide for your JEE journey, then you can use my code and you can join my courses. So my code is RDLive. Use RDLive to get your Unacademy subscriptions, and you will get 10% additional off as well. Alright, so that is it from my side. I'll see you guys day after tomorrow. Please remember, now the timings have become alternate days. Okay, so I will see you guys again day after tomorrow, and we'll carry the discussion forward from there.